let me call it reachability, which means how far you can go with a certain set of objects, and in the context of unitary groups. In the last class, I gave two explicit examples. One is that 2-qubit operations can be reduced to one qubit Euler angle decomposition and control naught. I gave explicit example of this. The other example I gave was 3-qubit operations. So actually I used the controlled U and not just a U. So let me just check. Yeah, I use control U, but that is fine. Control U. So these circuits I explicitly gave, and in general this control U can be broken down to the first part because it's a 2-bit unitary operation. So these are the kind of simplifications which can be done to reduce the complexity in terms of how many elementary gates you need to implement. Of course, when you factorize, the total number of operations will increase because you have many small operations instead of one big operation. But that is a part of the game, because the hardware implementation you want to only use simple operations. In particular, you can ask the question about why you could not do this 3-qubit trick in case of classical reversible computing, and that is connected to the fact that this was actually written as a control square with an operator which was U square, and it was broken down to this. If you want to use the what is called a Toffoli gate, which has a similar structure, which is a control square naught, and we could not find anything simpler and it could not be decomposed in classical logic, because, well, this argument tells you that what you need is going from here to here, square root of naught. And this operation doesn't exist in Boolean logic. But once you go to the full unitary group, you can take square roots of any operator, any unitary operator very easily. That is not a problem. But this is a discrete set of objects which involved only permutations, and there you can't do something like square root. There is one more thing I should mention, that most of the time I'll be talking about unitary groups with a further specialization that they are the so-called spatial unitary operation, SUN. But the general unitary group is a little bit larger. And the difference between these two is only a global phase overall factor, which always can be taken out because it commutes with everything else, and you can push it all the way to the final state if it is part of the algebra. And then in many of the measurements, that overall phase doesn't contribute because you are going to take a absolute value square of the final amplitude, and there it is a probability where the phase gets absolute value squared to 1. So this can be factored out, but you should keep that at the back of our mind because most of the theorems will be proven for this SUN, and then if there is an extra phase needed, well, we don't worry about it. But most of the operators which we use all the time actually involve that overall phase. They don't belong to this SUN group, and that is, well, quite trivial. So I will just write down various examples that, for example, this simple operator not, which is this is the off-diagonal one. It has determinant equal to -1. It's not inside SU2. It's outside because the determinant is -1. But that -1 can be taken out at the overall phase, and you can figure out what to do with it at the end, or maybe it will not matter in the overall calculation at all. But these phases are there in many of the operators which we wrote down, and since not is a very simple one, then can I easily write down all the polymatrices. This is just equal to the first polymatrix. They all have determinant -1. You can write down even this control knot, which I have to write a basis for it. So, okay. So 0, 0, 0, 1. 1, 0, 1, 1, and go some label. This is a control. This is target. And then what it does is, if the first bit is equal to 1, these two get interchanged, Otherwise, nothing happens. So it has a matrix that looks like this. These two are flipped. The flipping is just done by the NOT operation. But again, you ask what is the determinant? Determinant is -1. And even the simple swap operator in the same basis, well, what we are going to do is these two states do nothing, these two get interchanged. So it has a structure which determinant equal to -1. And there is a means. There are more. This one operator which was mentioned earlier, the so-called Hadamard operator, calculate the determinant, it is -1. And well, even this other control not in the opposite direction. So this. So if I now give a label which is the other way, where this is target and that is control. You need to get used to this kind of notation, so I'm just writing by brute force at this particular stage, so it doesn't matter. So here, these two states will flip, and the matrix looks like interchange of these two. Again, you calculate the determinant is equal to -1. And there is a simple reason why that -1 keeps on appearing over here, because these are all trivial permutation operations. At least this matrices, this is not permutation, but that's okay. With the extra property that if you square any one of them, you get back where you were originally. They are all square roots of identity. And because of that, the eigenvalues are +1 and -1, square root of identity, you can't have anything else. And you end up in a situation where the determinant is equal to -1. So all are So the point is that these operators will keep on appearing all over the place, and even though they are strictly not in SUN, we'll deal with them assuming nothing complicated is happening. That is true because the global phase can be factored out, or if you want to be mathematically rigorous, you put an I in front of these operators and then things will fall in place, simple things of that sort. So this is something which you need to kind of remember. And now I'm going to slowly progress about what are all the kind of sets of operators which we can look at. I gave the answer already that what we will need is a Euler-Engel decomposition of 1 qubit and C0, nothing more complicated than that. But there are various kind of options depending on how you want to discretize the whole group. And let me just give a kind of step-by-step labeling. So I'll start with just a discrete group, which we used in the Boolean logic. So this Z2 had only two elements, +1 and -1, and it can be very trivially extended to fourth root of unity which is this. All these number raised to fourth power equal to 1. And you can then look at the discretization on the unit circle, which is instead of looking at only particular roots, you can take any root of 1 and that will be value. If you want to discrete value of nth root, it will be e raised to 2 pi I divided by n. But you can generalize, and this group is all called U1, and this will describe a certain set of operation. It is not the same power as this SUN, but sometimes it is used with a name which is called real bit. It's not the discrete bit and it is not the quantum bit, it is somewhere in between, and it does not SU2 is based on complex numbers. Even though this is complex, the dimensionality is less. This is one dimensional and this is 2 dimensions. And this one is what we will use all the time for describing a qubit. It is more powerful than this real bit in terms of what are the kind of complicated correlation it can produce between different components. This one is not as powerful, and you cannot use it to cover the full quantum logic. Okay. That is just as a remark, but in some situations this has been discussed. In particular, this is the structure which you use to describe classical waves. The classical dynamics of waves, all you have is a amplitude and a phase. That can be described by this structure, but those classical waves do not generate the same complex correlations which qubits generate. Okay, so it's useful. It's not as powerful as the quantum dynamics. You should just keep that in mind. Okay, so then there is still a whole bunch of other ones which appear, and I'm going to quote their property. So there is a group called the Quaternion group, and it consists of the elements which are essentially identity and the three polymatrices, but with the extra factors of I thrown in such a manner that the squares of these three objects equal to -1. Okay. In the complex number here, you had +1 and -1, and there is only one extra number which squared to -1. Here there are three extra objects which all square to -1 and they don't commute. But they form a group under multiplication, and this Quaternion algebra is also used to describe a certain kind of operations. It is still something that can be covered by classical logic without too much trouble. It has non-commuting stuff inside it, but it's not that complicated. Then there is this something called a Clifford group, which is generated by H is this Hadamard matrix. It allows you to take square root of one of the polymatrices, and the 2-bit operations in this ones are the same as control naught. This one is still not as powerful as the full quantum algebra, but it has a special meaning in the sense that it can be described by a certain number of discretized operations, and they are closed under multiplications. So this it covers and this is the key label, that even though it involves some subset of quantum transformation, it can be simulated on a classical computer with polynomial effort. So it is not going to give us the full breakthrough which is needed to get a quantum advantage from the algorithm. The complexity class generated by all Clifford group transformation remains the same as what is there in the classical computer, because the conversion is only polynomial in terms of the effort. And the full group which can be covered is a kind of next stage. That is you need one more square root to be taken for this particular sigma 3, and then it is okay. Okay, these are all weirdities of playing around with the algebra, but you can demonstrate that yes, it can cover all the quantum operations once you take sufficiently many square roots of whatever is needed, and afterwards it's fine. The question is, if you don't take enough square roots, then you are not going to cover the full space. And remember, in all this progression, you can ask the same thing. What are the things you are doing? Are essentially, how did you generate I? Well, you generated by square root of -1. And that kind of a hierarchy is buried inside it. Everything next level, one more square root. Okay.
The square root of 47, we include both the minus I and plus I.
No, you take a convention, whatever it is. So if e raised to I theta, the square root you choose as e raised to I theta by 2. The other one is there, but it will appear in a different manner. Okay. So in the sense, you can write one square root, and the other square root will be its complex conjugate. That's okay. So you can ask, why this square roots kind of matter, but it's in some sense it is part of the discretization process that if you want to cover, say, the full group like this, all the numbers, you don't necessarily have to go to the full real range of theta going from 0 to 2 pi. You can rewrite this as just this. So by taking a power of some subset, you can reach all the higher numbers. And you can ask, when is this sufficient, when I can cover the whole range by just taking the powers, and the answer is rather straightforward, that when you take the power, you should not come back to identity, because otherwise it will become a discrete set like that. If you choose a theta, which is not a rational multiple of 2 pi, by sufficiently many number of operations of the same thing, you will go all around the circle. You will not come back. And what decides is the integer which is sitting in the rational number. It will, if you make an irrational number, it will generate the whole set. So these are the kind of questions which one can ask if you are looking at the question of reachability, and I just gave you several answers implicitly over here, and now I can demonstrate some of those things in more detail by describing the results which come from what is generically the description of these unitary groups, and that generally is described under the label of Lie algebra. So what does Lie algebra describe? It describes properties of the group generators, and what we have seen already is for SU2, these are polymatrices. So what are the things you can do by acting with generators some number of times? Okay. And that is the kind of question which you can cover by just taking various factors in some order to generate complicated structures, and we can write those relations for this algebra rather easily once you understand how they work for the polymatrices. It's just a very simple extension to higher dimensions, and the algebra doesn't look too complicated beyond that. The important point is the matrices in this unitary group have generators which don't commute, like the polymatrices. So you can use that feature to generate commutators of two operators in particular manner, and I will write down one of the identities. So what you can do with repeated operation. In particular, it is known as a Trotter formula, and it's an example. Trotter formula covers many different constructions. So I will use a combination which is involved with two operators and see what happen. So the combination goes like this, e raised to I a by root n, e raised to I b by root n, to some high power where A and B are some particular generators, and yeah, we will worry about these things only in the limit n becoming large. That is already enough to cover this question of reachability or addressability of how far you can go, but that is good enough. And now you try expanding this, because n is large, this is a small exponent everywhere, and you can expand just by Taylor series, nothing complicated. So the important point is that this minus and plus signs are arranged so that many things cancel out. So the leading term is just identity. The next term will be either A or B, the first power, but it occurs twice here with plus sign and twice here with minus sign, so that becomes 0. So what remains is actually quadratic terms, and one can evaluate them explicitly. It's 1 over n because it's coming from the quadratic parts, and there will be various contributions. There will be a whole lot of terms of the order of a square and b square, but they cancel out. For example, a square cancels from square of this, and then the product of these two comes with a negative sign. So it goes away. What survives is only the cross term, and that looks like this. Okay, with the and this can be rewritten as again by an exponent. So what has happened is you have acted by operations of A and B, and the net result is a commutator of A and B. And that means that you don't need to include all possible generators. Everything which can be constructed by commutator can be created from them. And we used that property in some way in the last lecture in describing the Euler angle decomposition of SU2. SU2 has 3 generators, sigma 1, sigma 2, sigma 3. But the Euler angle decomposition used only 2 of them. Which 2 you use is doesn't matter, but the third one is generated by the commutator, some complicated manner. And it's an illustration, so this is one useful property to remember, that even though there may be lots of generators, the set can be reduced by removing everything which can be generated by commutators. What else you can do? Well, when you go to a bigger group, you will find a lot of other tricks as well. And that comes from describing the action of this polymatrices in different subsets, but in a situation where they partially overlap. So the polymatrices are 2 by 2 matrices. When both the indices overlap, you can do the Euler decomposition. When they don't overlap, they will just be independent, but there is a in-between situation where one index overlaps with something and the other one does not. And that generates yet another kind of a situation which is interesting to look at. And I will again give the answer first and the description later. So and for that, let me just the calculation first. So let me take one of them, both of them, sigma 1 is good enough. But now, well, I'll just restrict myself to one block and the other one is 0, and take a commutator where the 2 by 2 block and 2 by 2 block here, they overlap in the middle index. Okay. And then, well, we'll just calculate it by brute force, see what comes out. So the first row, there are two terms. I multiply this with this, so there will be something here, and this one doesn't do anything, this one doesn't do anything either. So and now the reverse order. So this multiplied by this, nothing. This multiplied by this, third row is all 0. But this multiplied by the first one gives 1 here. It looks like this. And because it's a commutator, this one has a minus sign compared to that. And this can be rewritten in terms of another poly block, which we write by analogy. With the poly matrix, which is sigma 2. So what happens here is this one has structure of sigma 1, and by taking commutator of the 2, somehow you generated sigma 2. And this is a general identity. I can write it more symbolically. The sigma x ij with sigma x jk. This j is just to illustrate that one index is the same, but there is no summation over j, which is another convention. I'm not doing that here, but this is equal to the index which was common disappears and you get a sigma y on the remaining two indices. So this tells you that by having some combinations, you can even generate sigma y from sigma x, and once you have both sigma x and sigma y, you can generate sigma z, and that is all you need to cover the full structure of SU2. But what do you need to be able to do that is a larger structure where these objects are rearranged in different locations. And because I wrote sigma x, it is easy to identify what this will get buried into. They are generators of the permutation group. Remember, permutation group was the one which I described as a group for classical Boolean logic. So, given the classical Boolean logic, and on top of that, some structures to generate this Lie group kind of description, which allows commutators, you can do a lot. And this is buried inside, in some sense, the fact that to go to higher groups, just having C0 was enough. Remember, C0 has this permutation group structure like this. You don't need other kind of polymatrices. If you need it, you will generate it by various kind of commutators. So that is a feature of what can be called universality. We are just trying to find out the smallest number of quantum objects which can generate everything. Okay. And this all this analysis now allows me to formally give the set which does the job that we need. So the first thing which was historically pointed out, and there will be simplifications on top of that, is an operation which is called the Deutsch gate, and it is just described in terms of these sigma 1 or sigma x exponentiated, and let me put the factors right so it becomes real by the simple convention, otherwise the complex I will appear in various form, and this is minus I, so that let me make this one plus I. So when you expand it, it becomes real for the specific value of theta equal to pi. And that one is well, I think because it's half, it is pi. And the gate which he used was this control square R, and it had the same structure that control square naught. For a specific value, when you put theta equal to pi, this exponential can be written as cosine and sine, and cosine of pi by 2 will be 0, sine will give 1, and then this minus I here and plus I over here multiply together, it gives 1, so it just becomes equal to sigma x, which is the control square naught operation. So the argument of Deutsch was that this particular operation is universal. Why so? Well, one step is it generates this Toffoli gate. And so because it is already inside that, so it can generate all permutations, because Toffoli gate could generate all permutations by itself, as we have seen in case of the Boolean logic. And on top of that, it can generate any power of sigma x, because this theta is a variable parameter. And now you can see the combination of all those arguments, that yes, it can create all the single qubit rotations by just putting these two values equal to 1, no problem with that. It can cover permutations from sigma x. If you have multiple labels, you will generate sigma y by just permuting the indices using the Toffoli gate and multiplying them together. So you will get sigma y, and then once you have both sigma x and sigma y, you can generate sigma z by one more commutator of some question. We are not asking the questions how many operations it takes. We are just asking the question is whether it is possible to do it or not. So because of this, all these arguments, the permutations which will appear inside here are among the 8 dimensional states. So they are 8 by 8 matrices instead of the 4 by 4 in case of control naught, but we can juggle them around, and this construction is sufficient with permutations and this single sigma x to cover the whole SU8 group. And afterwards, so any higher qubit operation can be decomposed into this 3-qubit operations. We have seen that, for example, a control to the power n not could be decomposed in terms of 3-qubit operations by just recursively applying over a succession of the qubits. It was one of the exercises which I described earlier, and the same thing can be done if you have control raised to power some n naught. You simplify first to a Toffoli gate, and after the Toffoli gate is done, you cover the full SU8 group using this Deutsch formalism, and you have the complete coverage in terms of all the group which is involved. So this was actually the first example without realizing these extra features for which we give circuit over here, that yes, this was a 3-qubit some unitary operation gate, but we could simplify it first to control U and control not, and even the control U can be broken down to Euler angle decomposition and control not, and that is a much smaller set than whatever this particular operation describes. So, and this SU8 group can be so this is typically the set which is used in the description of most of the algorithms. Okay, there is a flexibility of certain type about whether you use control not or some other 2-qubit operation, that is dependent on the applications, and you can try out other kind of 2-qubit operations, no harm done. And some of them are useful in a specific hardware realization. And the 1-qubit rotations, in particular the Euler angle decomposition, is common. Everybody uses this in the description of various kind of algorithms. So this is actually the general analysis of the reachability of a unitary group. What is the minimum thing that you need? And you have, in some sense, a complete mathematical description. I have written down various results intuitively or by simple arguments. You want to convert it into theorems, you can do that. What is the caveat? The caveat is that this is the question of reachability. But how many operations you will need in practice? That is a question of the computational complexity. And yes, you can simplify, but if the simplification is too big, then you have not gained any quantum advantage. And that is a important specifications is yes, you can do that, and how many operations you need. So here there is a theorem. I give an arbitrary matrix, unitary matrix of a certain size. How many of these operations will be needed to be able to cover all possibilities? The general result is the number of operations is the square of the dimension. There is no shortcut available beyond that if you are dealing with arbitrary matrices. And now we can see the trouble. What is the size of the unitary matrix? 2 to the power of number of qubits. So if you ask a question that, yes, I have this good subset, 1 qubit and 2 qubit, I don't want anything more than that, I can break it down. There is no harm done, that any general UN can be broken down. But how many of those individual operations will appear? Exponential in the number of qubits. And that means that the algorithm in this particular strategy need not be efficient. To be efficient, what we want is the number of operations should be polynomial, not exponential. And well, the theorem tells you in this result, number of operations is a polynomial for only certain types of these matrices. And what do the matrice or evolution stand for? It stands for an algorithm. And this result tells you indirectly that some algorithms will have a good quantum description, while some other algorithms will not have. When it will be good? Well, if you can break it down, this general U, into polynomial number of 1 qubit and 2 qubit factors. If you cannot do it, the quantum advantage is not going to be present. It's very much a problem-dependent statement. So now you have to ask that if you have a general problem, make up this algorithm, can you break it down nicely into this small number of gates? And sometimes it's possible, sometimes it's not possible. Both the types of examples exist. And you can literally describe problems that some of them will get simplified, and some of them can say that it cannot be simplified. And this is the whole exercise now, to find problems where you have this simple reduction of the transformation that you need. And there is no what you call a recipe of doing that. It has all been an exercise of trial and error. think of some matrix, can you break it down? Well, if you can nicely break it down, you have a great work to report. If you can't break it down, well, try something else. That's bottom line. And what is the breaking down process? Well, it's a sequence of operation. So it's essentially a process of factorization. We're applying one operator after another. And that has an analogy what I said in case of a general Boolean function. It had lots of terms. When was it efficiently evaluatable? Where it was a polynomial, if I could factorize it nicely, then there was a improvement in terms of the complexity. If I can't factorize it, then all the terms had to be evaluated. There was nothing to be gained. So it's the same problem coming back in a different manner. We have a general transformation. If you can factorize it, you have an advantage. If you can't factorize it, it remains whatever it was. And it's a difficult situation in that yeah, you have all the new kind of algebra, but at the end of it, you're not gaining anything useful. So this is as much as I need to cover in terms of generic results about this question of reachability. But there is one more point which is important, and that is the question of error. And the question arises because of the structure which you are using for describing quantum logic. Everything is described in terms of continuous variables. And if the problem was in a discrete logic like the Boolean case, we didn't bother too much about the error because it can be very well controlled by what is called a bounded error prescription. That 0 will remain 0 and 1 will remain 0. If the fluctuations are small, you just put them sufficiently far away from each other. You have to ask the same question here, that can I develop a bounded error description on top of all those things when the operations are not perfect. They fluctuate a little bit. And then the question is, not only this is needed, I need to keep those errors under control. That if there are only polynomial operations, but each operation has a certain number of errors, what is the total error? And if you have done any exercise in numerical algorithms, that's the classical tricks of various solutions which you may have tried in Mathematica or MATLAB or any of those things. You will know that the common scenario is that the errors grow exponentially in the number of steps. That will again destroy this whole machinery, because you may have polynomial of number of steps, but the error is exponential in the number of steps, things are out of control. And so we need to figure out, in case of this unitary dynamics, how do the errors grow when you have many number of steps. And the good result is that the errors grow polynomially, or much more accurately, linearly in the number of steps when the operations are unitary. And that becomes a very important fact in designing the algorithms, that yes, you can have calculations which has finite number of operations. Finite means polynomial, and the error also doesn't grow any worse than that polynomial number of operations. So you need to formalize these argument, and for this I need to give some definitions. So let me do that. The result is not too complicated, but you have to write the definitions in a very transparent manner so that the logic is very clear. Okay. So it's a sequential operation, so what I want is some particular operation, some state at time t minus 1, some unitary operator, and I can put a label here as well. And it will give me some final state. And I need a approximate version, which I'm going to just denote by a tilde sign on the top. That if I don't have the correct state, I don't have the correct operation, what will I produce this? And then the answer is, what is the difference between this and this? Given the whole bunch of good operations and the approximate operations, and a common starting state, which I will just denote that phi of 0 is the same as phi tilde at 0. That's the initial state. So at the 0th step, there is no difference, but everything else can be different. Yeah. So let me just then define the result of a wrong operation at the last step. I had some state, I applied the approximate operator, it generated some perturbation. That's it, nothing more complicated in. And then I have the task of what is this final state with all the approximate result, and it can be written very easily as the exact state plus the error which occurred in the last step plus the error which occurred because of the one step before, which is there was an error and I applied a wrong operator, and what happens to that? It evolved and it continues all the way till the whole series it terminates at the error which occurred on the very first step. Okay. Remember, at the 0th step, there was no error. So after the first step, because there was a wrong operator, I generated E1. Then this E1 will evolve with all the wrong operations afterwards. Then there will be something else, E2 will appear at the next step. It will evolve with all the other stuff, and it will continue all the ET, which is the error at the last step, and that it basically gives me a total error which occurs, and this is just a recursive mathematical identity. Every step produces some error and it contributes to the final step by all the wrong operations acting on that error. If error is not created, then there is nothing going to happen over here, and that allows me to write the whole thing in a compact manner. That what I'm interested is in this. Basically some magnitude of this, which is well, upper bounded by the magnitude of each of all these error vectors. Why so? Because the result is just the sum of all the vectors. It will get its largest value where all of them are parallel. If they are not parallel, there can be cancellation and the number will be smaller. That's why there is a greater than or equal to sign. And the unitary matrix is there, and because I am writing in terms of the length of the vector, it doesn't matter because the unitary object will just rotate it, it will not change the magnitude. So, largest error for all terms, all errors. With all the number of whatever it is, it are all parallel, and now I can just a very trivial upper bound on this particular object. What was it defined as something over here, and I can rewrite the same thing in a different language. So it goes back to writing this u tilde and u in a different I'm just using this definition. Phi t is equal to the exact ut acting on phi t minus 1, and et is nothing but u tilde acting on that phi t minus 1. So I just write it as a difference of the two. And that now relates what I want, the difference between two approximate operations acting on the vector, and this is less than or equal to, well, two unitary operators, how far they can be. It's a norm of the size of the magnitude. So the largest value will occur where the eigenvalues of these things are going to be some e raised to I theta. and this phi equal to the eigenvector with the largest difference in the eigenvalues. That gives the upper bound. Okay, so you can factor out one of the UJs and write it as a approximate times the exact part, which cancels out and just gives the remaining part, and that will contribute the largest value when the eigenvector for the largest value again appears here. If some other eigenvector appears, then it will be smaller. So this is just a upper bound. So and that is a specification now which can be very simply written, that this quantity which I call the difference of the two vectors is less than the factor of t comes because there are so many different terms are summed up over here, sum over all the j, and epsilon is the okay, so let me call this largest eigenvalue is theta j, is epsilon is equal to maximum of theta j. I'm just getting an upper bound. And that is the point, that I have certain inaccuracy between u tilde and u, which is upper bounded by this value theta. What is the error in the result that I am going to get? The vector. But it is number of steps multiplied by their inaccuracy. So this is linearly in number of steps. And that is the linearity is the important part. It's not growing exponentially. So yeah, I will stop at this particular stage. I will probably describe this last bit once more in the next lecture, because it requires algebra is simple, but understanding, you have to get the meaning of this rather simple statement, because it's a very important result for describing complexity of the algorithm.